Welcome everyone. My name is Elisabetta Di Nitto. I'm a board member at Informatics Europe. And so I'm going to give you a very short overview of Informatics Europe, just to let you know about this association and what we do, and also encourage you to join us if you wish. We represent public and private research community. We are an association that includes departments from a large number of universities in Europe and also from some industry. We are focusing on research and education in informatics, and we try to create working groups, initiatives that are aligned with this main objective. Here we have the number of partners at the moment. So we have 155 academic institutions, 4 industrial members, and 34 countries from Europe joining the association. So as I said, we focus on research and education. We foster high quality research and education, we promote knowledge transfer and collaboration. Typically what we do in our annual conference is to run workshops that are aiming at facilitating the exchange of ideas among different department representatives in various concerning various subjects that we identify year by year. We also want to engage with society. We try to promote the presence of best practices and high quality standards in research and also in education and knowledge transfer. We are a group of volunteers. Essentially, as I say, the departments join the association, and representatives from these departments can decide to take an active role in the association. And of course, so we encourage everyone willing to take an active role to convince the department to join if the department has not joined yet, and to let us know their interest so that we try to involve you in one of our activities. We have a number of working groups, and these are the ones that are currently ongoing, focusing on education, diversity, ethics, career development. Policy recommendations means that every time we identify a specific issue that requires some recommendations toward our political stakeholders, we try to do so. And so there are multiple activities here. Now recently we started, we created a webinar series that is focusing on was initially focusing on scientific aspects, and in particular Erika's seminar is focused on, it belongs, let's say, to this category. But now we have also other categories of webinars on gender diversity, career development in particular. We have also a course on academic leadership development, which we are running regularly. So this is particularly good for, especially for young people. So if you are interested in our activities, you can check on our website or Twitter and LinkedIn. So let's move now to today's speaker. As I said, today we have the webinar by Erika Abram, and she is a well-known researcher, especially focusing on SMT solving, and in particular for real and integer arithmetic and formal methods for probabilistic and hybrid systems. But of course, she can say more about her focus much better than me. So I just leave the floor to her. And just a second, Erika, I stop sharing so you can now share your screen. And welcome to everybody, and thank you to Erika for this webinar.
Thank you also from my side, and welcome everyone. Unfortunately, physically, but it has also advantages, so we can be a larger group discussing about interesting topics. And what I would like to present to you today is introducing a bit SMT solving to those who do not know yet what it is, talking about its past, about state of the art, and also what might happen in the future. And because though 1 hour seems to be a long, but I don't have so much time to talk about everything interesting, I will stay at the high level and talk mostly intuitive and do not go deeply into technical parts. So let me introduce or motivate SMT solving on the traveler Eve's problem. Namely, now that the COVID lockdown is mostly over, Eve is eager to make scientific visits again and travel, but there are some restrictions. She has 100 travel wishes because we need to catch up with missed opportunities, but she is allowed only to make 5 travels currently. And as Elisabetta told us, ECSS is approaching fastly, so she wants to be there definitely physically in Madrid. And she coordinates a project where she also needs to visit one of the partners, A2 or A3. And she has some restrictions on cost and time. She has a restricted budget, and each travel has a certain cost. And she has a lower bound on the time traveling, and she has a certain duration for each visit. And now the question is, how can we solve this problem? And of course, you try to make it with pencil and paper, but with more complicated problems, it is not so easy. So here you can see an example how we can encode this problem logically by writing a formula, in this case over linear real arithmetic, explaining that for each of the 100 travel wishes, either it does not take place, expressing it with this flag AI, then we have no costs for travel I, by Ci equals 0, no time duration, or the travel takes place, in which case this flag is 1, and then we have the costs and time as specified. We can make at most 5 travels. We have to be at ECSS, need to visit one of the partners, and the costs must satisfy the upper bound, the time the lower bound. So now what is good on expressing these problems in a logical form? The good news is that there are tools that can solve the problems once encoded logically, and then from the answer, we can transfer back the answer to the original problem. And there are different types of tools that can do so. For example, theory improvers, constraint solvers, computer algebra systems, or SMT solvers. And these are quite disjoint areas from the scientific community, not so disjoint from the technology side. They do have some intersections, but because today I cannot talk about all of them, even though each one of them is exciting, I will focus on SMT solving. This is why, because we have our main research focus on SMT solvers. So let me tell you short first what SMT solving is, then a little bit talking about our own solver, of course, SMT-RAT. I will show you a few applications and at the end talk about future challenges. So SMT solving, its roots, it has, well, it is not that its roots has, computer algebra systems are the oldest from these technologies. As soon as computers were accessible, mathematical logic tried to implement the algorithms developed so far for a lot of mathematical computations, but especially also for checking the truth or satisfiability of logical formulas, with the main focus on arithmetic, given the mathematical domain. And these systems are very large, very heavy, of course, also very expressive. But once computer got very popular, another problem raised, namely when computers are produced in a large number, if there is a bug in the circuit design, then it is very expensive. So the people tried to develop techniques for verification, and this was one of the main drivers for working on satisfiability checking tools. And the first type of these tools, SAT solvers, were developed for propositional logic. And as I said, it is related to circuit verification, because in propositional logic, you can encode the existence of bugs, so of counterexamples to certain properties. Here I list only a few SAT solvers. It is by far not a complete list, but perhaps some of the well-known ones. So what is behind SAT solving? There is a standard input language, meaning that if you encode your problem in this language, then you can use basically all SAT solvers, because nearly all support this language. And it allowed also to collect a large benchmark library to test the tools, but also to make competitions and check which tool is more powerful on these benchmarks. Just to give you an impression, in 2021, so this year, there have been 4 tracks, so different types of tasks. And within this task, if I counted right, 18 solvers participated in different versions, so altogether 45 tools in the main track. There is a whole community behind it with SAT Live as a community platform, dedicated conferences, perhaps the main one being the SAT conference, journals, and so on. And I would like to give you just the idea, what is the basis of SAT solving? The basic idea is the following. So assume you have a problem and you have parts of its solution which you could plug in together combinatorically. So you have, for Boolean logic, this would be the resolution proof system, for example. You can derive proofs, but it is very tedious. So we try to search for something that is in practice more efficient. So instead of analyzing the problem and trying to find a solution logically, we explore. So for example, we start, if we have a labyrinth, we just start going in it. And if we arrive at a dead end, and we turn around, and at the last decision, we swap our decision to go in another direction. And you know, if you always go to the right, then at the end, we find the exit, if there is any. But sometimes it is good to have a light, to see that if I go somewhere, that I would end in a dead end, so I can avoid going in there. This is a kind of light look ahead. Not complete, so still it might be that something is a dead end, but I don't see, I will see it later. But at least it reduces the number of wrong trials. And only when we end up still in a conflict, in a dead end, then we use the proof system to explain which of our previous decisions has been wrong. Let's be a little bit more formal. So the exploration we call Boolean decisions, the look-ahead Boolean propagation, and the proof system is Boolean resolution, which we used for conflict resolution. I show an example how they work together. Assume we have a propositional logic formula consisting of 2 small clauses like here. We always start by propagating implications of previous decisions. We didn't have a decision yet, so we go on. We can decide now to explore, for example, try whether there is a solution when A has the value false. Now we might propagate, and propagation means here something lightweight that we can execute relatively fast to detect implications. And in this case, it might be that in a clause, that means in one of these disjunctive components, we have just one way to save its truth. Here we don't have it, but if we propagate here, we don't find anything. If we make a second decision, for example, assigning false to B, then you see that in this clause, the first clause, we must assign true to C, otherwise this clause is violated, and then the whole conjunction is violated. So we propagate and assign true to C, but then the other clause gets unsatisfied. So we find a conflict. This is the DPLL idea. And CDCL now explains what we did wrong by the proof system. Namely, this is the wrong clause, and it looks at the last implication. This literal was implied by this clause. So this literal is here false, negated. It was implied to be true in the other clause, so that it is not negated. Meaning that we can apply Boolean resolution to these two clauses. So we take the rest of the first clause and the rest of the second clause without the literal here and its negation in the other clause. And then we get A or B. And this is exactly what we did wrong, right? We assigned false to A and false to B. Here it is trivial. In other cases, it can really give you the point to the decisions or to the implied values that are really the reason for the conflict. And then SAT solving has been by this combination. It happened in the 90s, there where I started to write. So Chaff was one of the most successful solutions for this, introducing this DPLL-CCL approach. And then they got really, really powerful. So very large problems, practical problems could be solved, and these technologies could be applied in practice. And this motivated to extend the expressivity of the logic, not to use for proposition logic, but replace the propositions by some theories. And this is what is the aim of satisfiability modulo-theories solving, namely checking the satisfiability of quantifier-free first-order logic formulas over some theories. Also here, and this was a great achievement, a set of logics have been identified, and for them a standard input language was agreed, which is again the basis for benchmark libraries and for competitions also since 2005. And sorry, I forgot to change here the number. This should be 21. So this year there have been 6 tracks, and in the single query track I could count 19 competing solvers, and there have been like 28 or something like that non-competing ones. So they were just running, but for some reasons they did not take part in the competition. Now, I tell you how SAT solving works. How does SMT solving work? There are 3 main approaches, and I will tell you about all 3 a little bit the intuition, and I will show you an example how they work and propose also some extensions that we are working currently, which might be also very efficient. So let us start with eager SMT solving, where the idea is that we first, if we have the Boolean combination of theory constraints, then first we make sure that in the theory we don't have conflicts. So we solve the theory part such that we are left up with a propositional logic problem, and that we know how to solve. We have SAT solvings to solve them. So how to solve the theory and encode everything in propositional logic? I just show it to you on a small example. Assume we have equality logic. So the formulas are Boolean combinations of equalities, and these equalities over variables. When does such a formula have a solution? Well, if I firstly satisfy all the equations and the solutions do not contradict to each other. And we know that equality is an equivalence relation, so it is reflexive, symmetric, transitive. So if I encode those properties, then basically I can encode the properties of equality in propositional logic. So at the end, what we want to have is a formula in propositional logic, which is equisatisfiable with the original formula with equalities. So for example, in this case, I can say that all the equations are true by encoding the truth of the equations by a Boolean proposition, and then encode transitivity. That means, in this case, each instance, so here, transitivity means if x1 equals x2 and x2 equals x3, then also the first one needs to equal the last one, so x1 needs to be equal to x3, which is encoded here. And now this formula is satisfiability equivalent. So I check it, and if I find a solution, then also the original formula is satisfiable, otherwise not, and we see in this case it's unsatisfiable. So this is the idea of eager SMT solving. There are similar approaches for different theories, like for uninterpreted functions, bit vectors. If you have heard already the expression bit blasting, this is also based on this principle of floating point arithmetic and others. Now this was eager. Eager means it is eager to solve the theory. And lazy means it is lazy to solve the theory. So it's just the opposite. First, lazy SMT solving tries to find a solution for the Boolean structure of the problem, and only then it checks whether in the theory that is consistent. Let me show it also on an example. We have this input problem, and first we take its Boolean structure, also called the Boolean skeleton. So each letter here, each proposition encodes that the constraint above it is true. And now we know how SAT solvers work in the meantime, so we can try to explore. We assign false to A, which will imply in this case that B needs to be true. And now the SAT solver could consult the theory solver whether these two propositions, the corresponding constraints, are consistent in the theory. So this one negated and this one being true. And the theory solver would say in this case, fine, please go ahead, the theory is okay. And the SAT solver would continue, for example, assigning false to C, which would imply by propagation in this clause that D needs to be false. And the SAT solver asks again the theory solver, are you still fine? And the theory solver would detect no, we have a problem here, and it would give an explanation, which might be a subset of these constraints. In this case, this constraint alone is already unsatisfiable. So it would tell the SAT solver this constraint alone is not good. So the SAT solver would build a Boolean abstraction of it and learn at the Boolean domain. That's why it is also called the Boolean abstraction refinement, that the constraint D should not be true. And then it continues. Okay, so this is lazy solving. And eager and lazy are just contradictory in the structure, right? So eager starts with theory. It is the first, the main leader, and the Boolean follows. And in lazy, the Boolean is the leader and the theory follows. And then recently, there has been a new approach proposed, which turned out to be very powerful, in which we achieve the equal rights for Boolean and for theory search. And this is called the model constructing satisfiability calculus. I would also like to show it to you, the idea, on an example. You remember, this was our way to solve propositional logic formulas by combining exploration, propagation, and proof system in SAT solving. The idea is to do now something similar here. Same, right? Also in the theory. Let us explore also in the theory by making theory decisions. And we could propagate implications of these decision consequences by theory propagation. And if we run into conflict, somehow we also need to generalize our wrong guess to exclude in the future. And remember that in the Boolean case, if we run into conflict, we could just exclude the current path because we have finitely many. Now, if we go into theories, into arithmetic theories, or others that have infinite domains, it is not sufficient anymore just to say, okay, we guessed wrongly, don't do this one, search for something else, because that would not terminate. So we need a kind of generalization of wrong guesses. And I show you on an example how it could look like. Assume now we have a formula in which certain constraint, assume a polynomial constraint over the reals is involved. And now we propagate in the Boolean case. So we assign in the Boolean case that this constraint should be true. Okay. And now we move to the theory. And the theory might now also decide, well, let us check whether we have a solution by also exploring values in the theory. So what about choosing a value for x? In order to don't make very silly guesses, we propagate, we check, well, can I see already that some values for x might not work? So I do not choose them at all. And whereas in the Boolean case, we did it by propagating in clauses, searching for unit clauses, which had just one last possibility to be satisfied. Here, we look at univariate problems. So if I substitute my previous guesses in the constraints, then I collect those constraints which has just a single variable left. Because for univariate polynomials, we can still check their consistency relatively lightweight. Okay? But here we have no univariate constraints, so we can choose for x whatever we want. Let us choose a nice number, 1. Okay, we go ahead and we want to choose a value for y. But you recognize that if I substitute 1 here, then my constraint gets univariate in y, and it gets the constraint, becomes a constraint y squared less than 0, which is unsatisfiable. And we could recognize here by this propagation, and we have a conflict. And now you see what I meant. If we would exclude x equals 1 from the farther search, it would not help at all, but because I could take 1.1 and 1.01 and 1.001, so hopeless. We need a generalization. And in this case, one generalization meaningful could be to learn the clause that if this constraint holds, then x should be negative. Because only in that case, this left term will be have a negative coefficient, and because this is positive, it could be negative. Now, how to generate these generalizations? I show it to you on a simple example. We move back from polynomials because they are quite complicated, and I will not bother you today with that in this talk today, though this is beautiful, really. So if you like math, there is so nice algorithms and so elegant solutions. If you are interested in it, I'm happy to discuss at another occasion. But now I remain simple, also not to be in the need of introducing deep mathematical contents. So we remain by linear real arithmetic. And Fourier-Motzkin variable elimination is one possibility to solve such problems. I show you how. So assume now we compare lazy SMT solving with MC-SAT. We start with lazy, meaning at the SAT solving, we already have a solution for the Boolean structure of the problem. Assume these constraints should be true according to the Boolean solution. And now we ask a theory solver, are they together consistent? The theory solver says, well, this is a linear real arithmetic problem. I know the Fourier-Motzkin method. I take it to solve it using the following observation. Now, if we want to choose a value for x1, which constraints apply? And because these linear constraints are linear, I can always bring x1 to one hand side of the inequality. So here we have already on the left hand side an expression which is a lower bound on x1 here also, and here it is an upper bound. So x1 should be at least x2, at least 2, and at most 2x2. And we know that we search for a real solution, and the real domain is dense. That means as long as the intervals defined by the lower and upper bounds, so between the lower and upper bound, there should be still, at least they should be equal, but the upper bounds should not be larger, smaller than the lower bounds. And as long as this is true, there is always a value for x1 in between. So let us state this. We say that this lower bound is less or equal this upper bound, and again that the lower bound 2 is less or equal to x2. So now forget the first row by x1. If the constraints at the x2 level, these three constraints hold, then we know there exists a value for x1 which satisfies it, right? That's why the Fourier-Motzkin variable elimination is called variable elimination, because we reduce the problem to a problem with one less variable. And then we continue. Now we simplify these constraints, and from this we collect again lower and upper bounds on x2 and compare, saying that all lower bounds needs to be less or equal all upper bounds. And what we see here is when we eliminated all the variables, we get only constraints with constants, which we can check. And here we get a constant constraints which is not satisfiable, 1 less or equal 0, this evaluates to false. And if we can derive this, meaning that one of the intervals is empty, meaning the problem is unsatisfiable, and we can even collect those constraints by going up in this tree from the false constraint to its parents, we can determine which constraints conflict to each other. So the problem is unsatisfiable even if I remove this constraint. And now the series solver here, using Fourier-Motzkin, can return as an explanation to the SAT solver that these three constraints should not hold together. Now again, we build the Boolean abstraction, and the Boolean solver tries to find another solution which satisfies this constraint too. This was lazy SMT solving. Now let us consider MCSAT, the model constructing satisfiability calculus, where the Boolean and the series solver are both equal, and also the series solver can use exploration to solve the problem. Assume again that at the Boolean case we make the same decisions such that we have a comparable problem, and now the series solver starts, and because it can, now it also tries to explore. It asks, can I choose a value for x2? In order to make smart decisions, it checks the univariate constraints in x2, in this case x2 less or equal 0, and chooses a value which satisfies this. This is possible, and in order to have a nice number from the interval minus infinity to 0, perhaps we just take 0. Now we continue. Substituting 0 in the remaining constraints give us possible domain for x1. It should be at least 0, at least 2, and at most 2x2, which is also 0. And you see it is not possible because 2 is a lower bound, 0 is an upper bound, there is nothing in between. So now by exploration and propagation, we have found a point, two conflicting constraints for which we can apply one resolution step, Fourier-Motzkin step, to exclude this guess from future search. So we generalize this wrong guess x2 equals 0 to a constraint that if these two constraints are true, then 2 should be less or equal to x2. So simplified, x2 should be at least 1. And now we learn this constraint, okay, as a clause, and apply Boolean propagation because these two are true. It will imply that also this constraint is true. So now we have one more constraint that should be satisfied, and the theory solver tries again. It has backtracked from the wrong guess and again tries to assign the value for x2. And it considers the univariate constraints, which are the two red ones, and wants to satisfy both with the assignment, which we see unfortunately not possible, and explain it by applying again the Fourier-Motzkin step that this lower bound should be less or equal to this upper bound. Otherwise, the interval is empty and I cannot choose any value. So that means if these two constraints hold the two red one, then one should be less or equal to 0, which is false, means the two should not hold together. We learn this again, and then we find out that with these Boolean constraints are unsatisfiable together. So let us compare now these two solutions. On the top, you see the lazy SMT solving part, where we derived the whole Fourier-Motzkin steps in the theory solver, detected unsatisfiability, and returned to the SAT solver. So all this tree is generated in the SAT solver, in the theory solver. And the SAT solver does not see anything from it. In the model constructing satisfiability calculus, they are both working with exploration, propagation, and resolution in the Boolean and in the theory part. That means here you see that the exploration and propagation saved us work because these two constraints did not need to be derived. Actually, this exploration and running into conflict, the fact that we run into conflict means that we reach the part which is needed for the proof of unsatisfiability if the problem is unsatisfiable, or where we have a dead end, so we cannot continue. So we will not derive any information that does not lead to conflict, that is not necessary for an answer proof. This is the smart part in MCSAT, and that is what it makes so successful. And it is transferable also to other domains. For example, if you have counterexample guided abstraction refinement, this is a quite similar idea. So you have a system which is too complicated. Now you make an abstraction from it, reducing the effort for solving, and then it needs to be over approximating, and you try to solve it. And if you have a solution for the abstraction which does not satisfy the concrete part, then you generalize this spurious counterexample and exclude it from further search. This is something similar, but in the logical satisfiability checking approach. And same successful, but the problem is that from these cases, in real problems, you have a lot. And for each case, you need to learn a clause. And for each clause, you always need to apply propagation. And these constraints will be propagated even though they are not relevant for the current part of the search. And even though we can also forget them, they are, from a certain problem size, they kill. It is just too much. So now I move away from state of the art and tell you one of our ideas, how we extend it in certain directions. And the idea is to do lazy SMT solving as before. So we search for a Boolean solution first, and then we do theory solving. But we do this in an MCSAT style but without learning clauses, but remaining the bookkeeping locally in a data structure. And I show you an example what I mean. The same example, we have these Boolean decisions, and now the theory solver should decide satisfiability. So again, now the constraints are fixed, we start exploring. The same as before, want to choose a value for x2, it should be non-positive. So we might choose 0, and we get that then we don't have a value for x1. We derive the information, but we don't learn it. We don't take just this piece and put in a big bag with all the other pieces, but we remember it in a derivation tree, and we just continue by remembering this tree. So we can reduce, simplify this constraint, backtrack, and then continue the search as before. Again, now we cannot choose a value for x2 because the two constraints are conflicting. I can derive it, and I'm done. In the theory solver, can again collect the reasons and get back this explanations for unsatisfiability. So again, to put all three together to see the differences. Here we are in lazy SMT solving. A theory solver derives all the Fourier-Moskine steps. Here we are in MCSAT, where exploration in the theory is guided by propagation, and if we guess wrongly, we generalize and learn that under the given constraints, certain guess should be corrected. So here we learn constraint, and in contrast, in this third approach, which I call exploration guided theory solving, we can do similarly, but we do not need to learn clauses. We remember this structure locally in the theory solver, and then can apply this also in a lazy SMT solving approach. Okay, so you can say, well, linear arithmetic, this already we know, there are LP solvers doing this, so why do you invest your time? Actually, we do not do it for linear. I just illustrated it. We do it for polynomial constraints. And a very short intuition how that works, because I really cannot go there in the depths, but I show at least a little part of it. Assume we have a polynomial, like here. So it is very hard to see whether, for example, this polynomial can be negative unless you see this graph. But typically we don't, right? We just see the polynomial. But we can observe that if I knew the zeros of this polynomial, then I could just choose between the zeros, samples, and then substitute all these samples into the polynomial, compute the sign of the result, and then I can see. And each univariate polynomial has finitely many possible roots. We search for real solutions, so real roots, and this makes the thing decidable. And the good news is that I cannot compute the zeros, but I can symbolically represent them and compute with them. So this problem we can solve. It gets more interesting in higher dimensional cases when we have multivariate polynomials. So here, how to interpret these is I have constraints, for example, a green constraint, polynomial compared to 0. And this green line are the points where the polynomial evaluates to 0. We call it its variety or zeros. And this greenly shadowed area is the area where this polynomial sign condition is violated. So for example, it should be larger than 0, but it is less than 0 in this area. And similarly to the other constraints. Now for these polynomials, the basic idea how we can generalize wrong guesses is the following. Assume this red cross here is a wrong guess for x, because you see that here in this area, the red constraint is violated. Here, the blue constraint is violated, and on the top, the green constraint is violated. So there is no extension in the y dimension. And now from this x value, I can move to the left and to the right as long as the number and the order of the zeros remains the same. That means these lines do not cross each other. Because as long as this holds, we are in sign invariant regions. So you see, moving this point to the left and to the right still does not change the sign of any of the constraints, because in order to change its sign, I need to cross its zeros. And then I can generalize it to this area, the gray one. And this approach is called the one-step construction based on the cylindrical algebraic decomposition. A very nice method, and actually up to now the only complete method for real algebra out there that is implemented in TOOS. And later there have been an improvement of it, generating a larger cell by neglecting some of the constraints that are not relevant. And what we did is to enlarge it even further by also neglecting information that is not necessarily necessary for satisfiability invariance. So here it is not about sign invariance anymore, but about truth invariant regions. Okay, so if you get interested, get in touch with me. I'm happy to talk more about it. But now for the moment, a few words to our SMT-RAT solver. The motivation was when I started my own research in 2008, quite a few years ago, then there was no SMT solver for real algebra yet. For linear, yes. For nonlinear, no. And then short after Z3 came out, but then we were already working on this topic, and I was fascinated from the elegance of the decision procedure despite this complexity of the topic. So there are problems that look so nice and simple, and they are so complicated. And then because there are computer algebra solutions, like the cylindrical algebraic decomposition, the question was, can we plug them into the series solvers as a decision procedures? And the problem is that certain properties need to be satisfied, like working incrementally, generating explanations, and so on, which original methods did not do. So then we started to adapt methods, make them satisfying these properties, and then on the way, sometimes we detected new algorithms which are based kind of on the others, but they have a different nature through adaptations. So based on that, we implemented our SMT Red library. It is a C++ library. At the heart, there is our own main tool for real arithmetic computations, but we can also plug in other methods for polynomial computations and so on. And the modules of our solver are using this CARL in the heart, and these modules can be plugged together to a solver using strategies. What are the modules? This red one is the largest one. This is also a focus. So there we have the most modules, and we put in the most work. And this is real algebraic decision procedures. And actually, we implemented nearly everything that is available as a decision procedure. But we did also a little bit in the other directions. You see here the cylindrical algebraic decomposition. This is one of our main focus. And now these modules can be plugged together to an SMT solver by certain strategies, saying if the problem has a certain property, they use this module, otherwise use the other module. And the modules can again hierarchically call other modules on sub-problems, and again can branch on conditions. And with these conditions, we can also start parallel backends to solve the problems simultaneously. Now, having told you what SMT solving can do or how it works, let us go now how we can use them in practice. And SAT solvers are so widely used, I don't talk about them. But SMT solving are also very widely used for program verification, for verification in general, for solving combinatorial problems. And there are so many applications. I will focus a few applications made by us. So I will not talk about the applications of others. But if you just Google, you will find a lot. And every main conference has each year submissions on applications of SMT solvers. So what are applications? How do we use SMT solvers? As at the very beginning with Eve's traveling problem, we want to solve something and we need to encode this problem first logically. And then we can use SAT and SMT solvers to solve the logical problem and then transform back to the solution to solve the original problem. And the good thing is that we have this standard input language. So you encode once a problem, then you can choose the solver. So you can plug in your problem to several solvers and look which one succeeds the best. The bad news is that the encoding does matter. So you do not just need to encode it somehow, but the SMT solvers need to like it. So for easier problems, that is not a problem. Encode it as you want. But if you have hard problems, the encoding does matter. So because I have little time, let me show 4 examples for applications. One is planning. You have a set of robots here, actually 2 teams by 2 colors. They are distinguished. And each team needs to work with 3 robots collaboratively by producing certain products and delivering it. The orders come on demand during the run, and producing a product needs to go to different production machines, get some pieces somewhere put in there, after bringing partial products to other machines and so on. So it is a challenging combinatorial problem. And state-of-the-art solutions for planning are rule-based, meaning that the programmers solve the problem by saying, under this condition, the robot should do that. Under that condition, the robot should do something else. And we try to solve these problems using SMT solving. And if I say the encoding matters, I mean, we really had a hard time to come up with a solution that scaled better than the current solutions. And it is not only that it scaled better, it had more optimal solutions because we could plan for several robots collaboratively, whereas the rule-based approaches could not do so. So we are very happy that we could show that SMT solving is powerful enough also to support in this area and find plans that state-of-the-art approaches could not. Another possible application area is in product line construction and scheduling. This was a collaboration with Bosch, where it is about products are produced in product lines, so consisting of stations, one after the other, executing certain production steps. And these product lines, there are different types of product line with different functionalities, being at different parts of the world. And now the problem is that the ordering should be scheduled on the product lines by satisfying certain conditions. Of course, for example, delivery distance or customer preferences should be satisfied, but also to be efficient, a product line should be either fully used or not used at all. So the target is 0 to 80%, either 0 or 80% occupation. We need a long-time scheduling. We need also plans to build up new product lines or close them if they are not used. And this is a hardly computationally very challenging combinatorial problem. So we developed an SMT encoding such that this problem could be solved very efficiently. Another example is parameter synthesis. So you know, for example, you have a system and you would like to test it, and you're not sure which test cases you should use. And one solution for it could be, for example, that you have a model and a target which you would like to simulate, and then you do the following. Because here it is too complex to analyze, you make an over approximation or a close enough approximation of your system, logical encoding for the system and for the target. And now you have a parameter domain, D, which is basically what you can test, so the input for the system. And then you can check whether your system execution can reach the target within the domain, and whether the system execution can violate the target within domain. And then there are two solutions. Either, if I take any parameter here, it will either lead to the target or not. And if all points lead to the target, then this first formula will be satisfiable, the second one unsatisfiable. And in the other case, perhaps all points satisfy the second one, but none of them the first one. In this case, I know every point here leads to the target, every point leads here not to the target. But sometimes the domain can be mixed. So some points lead to the target, some points not. So both of these problems are satisfiable. Then I can split it and check both halves separately. And this might lead to this classification of the state space of parameter space like here. So I can get green areas which tell me all of them lead to the target. Red is non-interesting, none of them leads to the target. And the boundary is the white one where it might, but not necessarily does so. So now if I want to test, it is good to take the points from the green area. And the last application I would like to mention is reachability analysis for hybrid systems, where we represent state sets of a system which has some continuous dynamics, but also controlled by a discrete controller. So it has also discrete steps. And for the analysis, we need special methods. And the state sets are represented by geometric objects, like, for example, by polytopes or polyeder. And in order to make computations, set operations on these, or linear transformation and so on, we need also to compute with linear constraints in an exact matter. And there we also use SMT solvers. So now I'm nearly at the end. Let me conclude with some future challenges. Firstly, if you want to use SMT solvers, you have the standard input language and the benchmarks, so you can see how to use them. They are quite good already in user support. Most of them have some user's manual. You can use some of them online, some of them command line. Some have programming interfaces like C++ or Python. And more or less, you can use them as a black box. It is good if you know a little bit how they work inside, because then the encoding can be better, or you know which tool you can use for your problem to have something fitting. The nice and also the challenging part is that they are algorithmic as well as practically complex. So in 21, in the category for real algebra, there have been just 6 solvers from all over the world. And that shows that this is a challenging problem. And Z3 is from Microsoft, but most of the academic tools, most of them are academic tools, and not yet in the central focus of funding agencies. That means that we have many more ideas than we can implement. So we would need more resources to proceed further. But still, there is a lot of activity going on. One of them that is exciting currently is proof generation. So if you have an algorithm that is implemented in SMT solver, you have an input problem, get a solution. And in 21, in nonlinear real algebra, none of the tools had any bugs discovered. So they are reliable, but of course, bugs can remain undetected for a long time, so it is better to either substitute the solution to check whether it is really a solution, or get the proof of unsatisfiability, which you can certify using a theorem prover. And for example, CVC 5 is now on the way to generate such certificates. And also new developments is to have novel functionalities. Model generation is nearly all the solvers can do, but for example, model generation for real algebra is still non-trivial. Explanations of unsatisfiability, not necessarily in forms of proofs, but in unsatisfiable course. So basically telling the human in an intuitive way what is wrong with the formula or interpolants. This is also content of current research, and some solvers can also optimize, but also that the functionality can still be extended. Also, the support of quantified formulas is restricted, so quantifier alternation and quantifier elimination to get a symbolic description of the whole solution space is also not yet implemented in SMT solvers. And of course, scalability is a good point. Here I mentioned some interesting approaches to improve scalability, and especially machine learning also is a raising area, but it is also very challenging to apply machine learning in this context in a meaningful way. And I teach also satisfiability checking course. I think we need much more from teaching in this area because we need more young researchers who are interested in this area in academia as well as industry, but it has high requirements, combined skills, and I do think it is an optimal area for girls, but we have so few. So in research, there is nearly no girl in this area. So girls, if you listen to me, look at this area and make a PhD here, because this is really something for people who like a good mix of math and applied science. It is also very popular in my course currently, which has just started. I have around 400 students, and it is an elective course. So it is popular, but also challenging to teach because it is a complex topic and for students with diverse background, it is hard to teach, and there is also restricted availability for teaching material. So we would need more books that help us to teach. I am at the end of my talk. I'm a bit over time, but we also started a bit later, so I hope it is okay. And you are wanted if you would like to contribute either to the development of SMT solvings or providing new benchmarks for the benchmark library that are attached to some of your problems, or if you have applications, then you can join our community. It is really a very active, very nice, very communicative community, so everyone is welcome. I thank you for your attention, and I'm happy to answer some questions if there are any.
Yeah, in fact, there is one question at the Q&A. Did you see that, Erika?
No, because I have the full screen, so.
Okay. One question from Thomas from University of Ulm.
Yeah, if you want, I can read it for you. But
yes, please, that would be great.
Okay. So first of all, thanks for the great talk. I have heard that meta solvers have been excluded some years ago from SAT competitions as they have been too fast. Are meta solvers also available for SMT solving?
Yes, indeed. So this is basically the virtual best, right? So you let everyone run in a portfolio, and then the fastest is the winner. And they let it run always for the last year's solvers, but they do not take part in the competition. So they are running, but not participating. And indeed, they are very, very strong, which shows that the approaches that are used are kind of orthogonal. So still, it is not that the best one is always the best. There are also problem types where others are better. So yeah, if you want to use for your problem, I do not need whether it is accessible on StarExec, where the competition was running. Yes. Also another point, if you go to StarExec, if you log in there, then you can also see and have the solvers there. So you do not need to install all of them independently. Also a good tip.
Okay, and then we have another question by Nikolai Shilov. I hope I pronounce it well. So the question is, real arithmetic is fine, but we need to verify properties for programs that use floating point computer arithmetic. What can SMT offer?
Exactly. So this is the bit vector arithmetic theory, where we can encode floating point, for example, as bit vectors, and then there is a logic and there are solvers that are dedicated to that. And for example, CBMC uses this bounded model checking with floating point arithmetic, so exact encoding for C programs. And for example, in Simulink, design verifier, you have also a solver beyond it that uses SMT solving for unrolling the Simulink model. And then there is an automatic transformation to C code from Simulink. And this C code can be also checked by the, I forgot the name of the tool, BTC. BTC is the name of the tool, can be checked. And that uses bounded model checking for C code for really at the bit vector level. So yes, there are solvers doing that, and this is a very important point.
I have a question, Erika, that is probably silly, but the question is, I am getting kind of passionate for aspects related to quantum computing, and I was wondering whether you can elaborate on the relationship between quantum computing and SMT solvers, SAT solvers.
Yeah, so the question is not silly, but I do not know the answer. I think quantum computing is so young, so fresh yet. At least to me, it is not clear which impacts it will have on this area. But of course, if you talk about exploration and then quantum computing, where you can basically represent sets or a lot of things simultaneously better, then perhaps there are new possibilities which will reduce the complexity. Also, it is interesting to mention that arithmetic problems are long known, right? The history is not since yesterday. And for real algebra, so these polynomial problems, the complexity is, if it is existential, so just satisfiability without quantifiers, the complexity is singly exponential. And this CAD method, the cylindrical algebraic decomposition, is doubly exponential. And there is still no method in practice that implements this. That is a theoretical approach, a single one, which implements the bound. Let us go to linear algebra, because one says, nah, LP solvers are so powerful. Yes, but simplex that is used is also exponential for conjunctions of constraints with a complexity bound being polynomial. Also, a single approach, ellipsoid method, can implement the polynomial bound, but it is in practice less good than simplex. So therefore, still simplex is used. So what I want to say is, there are a lot of challenges, and I do think that in the next decade, there will be good push and good development here. But it is not that everything is taught here and everything is known. So if someone likes this area, there are a lot of PhD topics yet.
So we have actually a lot of questions now. There is Leopoldo Bertossi who is asking, what do you think of the use of for SMT of answer set programming? I understand that they are powerful for SAT, and the logical part can specify some theories.
Yes, so answer set programming, as I said at the beginning, there are these different approaches and the solutions are related. So if you want to compute the answer sets, somehow you need some quantifier elimination approach. Okay, so you need to compute answer sets, as the name says, and SMT solvers currently are not suited to do so. So they can compute single answers. Some approaches can generalize the answers to an answer set, but not to a complete answer set. This is like in SAT solving, you can have all SAT, where you can get all solutions. There are tools doing that. In SMT solving, I'm not aware.
Okay, and then we have other 3 questions. The first one by Joan, sorry. I saw that there is a theory for sets in CV-C4, but what about other structures like functions, relations, or even data structures such as stacks or trees?
Yes, so you have some like sets, you have arrays, and other data structures, only basic data structures that are used for program verification. If you have more, then you need to encode them in your encoding. So for example, trees, and so you can, trees of bounded widths and lengths, you can still encode in the encoding. I do not think that SMT-lib has a support for that, but they can be encoded. So a lot of things can be encoded. Of course, if you go like stacks and so on, then it gets, yeah. So bounded recursion is still okay. Again, you can encode, but then, yeah, it gets complicated. But you can look at the SMT-lib webpage. There is a tree of logics which are supported, and there are also examples for them. And these logics that are supported, they have a description like a textual axiomatization. Okay, so which axioms should be satisfied by this logic, and then the tools that solve them, the solutions should satisfy those axioms. So it is a kind of informal axiomatization. And then also the operators are defined which are usable there and so on.
Okay, and then we have a kernel of an SMT solver been formally specified and verified?
I do not think so. I do not know of any which is formally verified. But for example, CVC generates these proof certificates, so it can be then checked whether the answer is correct. And I do not say that they are not verified. I just say that I do not know any. Like in theorem proving, you have when this trusted kernel, right, which is verified. And then you can derive new things upon that. And if only use this trusted kernel in your derivations, then because you just build up change, it should be everything correct. I do not know of anything like that in SMT solving. So this would be also very interesting to look what is the minimal amount of functionalities that needs to be verified in order that I can state that my tool is correct.
And then Italo Oliveira is saying, may you please talk a bit about the computational complexity of SMT problems?
Yes, so the SAT problem itself, checking the satisfiability of propositional logic formulas, is already NP complete. So knowing that, you know, it is a sad story. Unless P equals NP, we will not escape NP completeness. And if you take quantifier alternation, for example, then it gets even worse. But in practice, it is really, really impressive how big problems these tools can solve in acceptable time. So talking about the computational complexity makes you sad, but looking at the tools working, I don't say that everything can be solved, right? There are the boundaries, but still very relevant problems can be solved in practically acceptable time.
Okay, and then Lorraine Munier is asking, what about quantitative SMT solving, meaning giving an approximation of the number of solutions for an SMT formula?
Yes, so if you have finite domain or discrete domain, then you could imagine doing something like that. If you move to dense domains like the reals, then of course you cannot count anymore. And at the end, I showed you this parameter synthesis, which gives you the satisfiable and the unsatisfiable regions. This could be something like that. Yeah, so in the linear case, it is still easier to generate solution sets, but in the nonlinear case, it's challenging. And what we can do by computer algebra systems is quantify elimination. So basically, describe a set of parameters for which you have solutions. This is one of the directions where there are also developments in SMT. But directly counting the number of solutions for SAT, yeah, you have this OSAT, which tells you all solutions. For SMT, I do not know about it. Perhaps also because there the number of solutions is so high that just enumerating is hopeless. But a very interesting and very important point somehow to not to get just one solution, but to have a feeling of how many are there. Yeah.
Then we have another question. Are there applications of SMT solver for open mathematical problems?
Yes. So what is challenging in mathematics also, there are problems where you have a combinatorial part and somehow theory related part. So there are some very interesting approaches which try to find such combinatorial parts in problems and then encode this combinatorial in SAT SMT, and then using computer algebra to check the harder parts as theory solvers. So in that direction, there have been several open problems related, for example, to matrices of different types, where you reach another number to which you can show something. Also, yes, so there are interesting works in that direction also for open mathematical problems.
Okay, so thank you very much, Erika, for the very nice presentation. I am sure that this recording will be really appreciated by many people who want to approach this specific area. So I'm very glad that you have been giving this talk. And thank to all the participants who stayed here with us and asked interesting questions. So
yes, thank you for your attention.
Thank you all. And of course, we will make available the recording pretty soon as we can do it logistically, essentially. Okay, so thank you all, and have a good night. Bye-bye.
Bye-bye.
Bye.
Bye-bye.